we talked about power? What if we talked about power? What was it related to? Try to figure out what it was. There is motion involved when you generate power. But there was a topic that we studied that was related to power. Now momentum. Energy. Remember how we talked about power right after conservation of energy? We talked about kinetic energy, potential energy in a spring, conservation of energy, and then power. How is power related to energy? Anthony again, unless others can look at their formula sheet, that might help you. Look at your formula sheet to see how power is related to energy. It's a capital P, right? It's a capital P. Ellie, what do you got? You said, oh, like you saw it. You're like.
Is it like work over time?
That's it. Very good. Okay? And we also said that you could think of work as the change in energy over time. Okay, we could think of either representation for power. When we spoke about these earlier in the year, we were talking about horsepower at one point, and the unit of power. Anybody remember the units for power were? What was the unit for power?
It's like joules per second?
Yes, which is a what?
Watt.
There it is. Okay, joules per second or watts? Very good, friend. Okay, watts. When you see a light bulb, what do you read on it? It tells you how many watts. How much power is it consuming? So, power, like yesterday, we talked about, what was it that was a rate? We talked about something that was a rate, not yesterday, 2 days ago. What was a rate? An example of something that we just studied that's a rate.
Voltage? I mean, current.
Current is the amount of flow in a given time period. It's a rate. Well, take a look at this. Power is divided by time, isn't it? So power is actually a rate. And it's really important later in this lesson where this is going to come back. Energy is literally what you use. So if my phone needs to charge, I plug it in the wall. I get a certain amount of energy and then it's charged. Power is not what you're getting. Power is the rate that the energy is flowing into your phone. You see the difference? Again, let me make this clear. Energy is the actual physical quantity that you're getting from the energy source, whatever the power source. See, I say power source because we do that so much. It's actually an energy source. But the power being delivered is the rate at which you're getting that energy. So when you get charged for electricity, parents, maybe you live in a house. Any that live in the suburbs know this for sure. If you live in the city, if you have an apartment, it might be part of your whatever. But if you get an electric bill in general, it's usually from a power company. It really should be an energy company. And they've started to rename things, and they've actually done better, which is like ridiculous to think about. But you're paying for energy. You're not paying for power. Power is the rate that energy is coming to your house. That's all it is. Okay, the power is the rate at which it consumes energy. So when you buy light bulbs, do you want your light bulb to consume a lot of energy? Why not? It might die quicker, or what else?
Cost more.
It costs more. You pay more, right? If the power level is higher, you're consuming more energy. So when you get a bulb and it says 40 watt, 60 watt, 20 watt, now there are bulbs that are like 10 watts, and it says the brightness of a traditional 40 watt bulb. Why is that? There are 12 watt light bulbs now that say on the label the brightness of a 40 watt bulb.
It's 4 times more efficient than
Exactly. It's about 4 times. 12 to 48 would be 4 times. Okay? Old school bulbs are not efficient. Regular incandescent Thomas Edison light bulbs that you are traditionally seeing are not efficient. So you used to be able to use them, and they would consume a lot of energy because the power that they used was 60 watts. Then they went down to 40 watts and were able to still keep the brightness. But with these old bulbs, if you're at 12 watts, it's not even bright at all. It's like a little tiny, the bulbs on like a, in Christmas time, people have those little people in the window that are like moving like this, and they're like holding a little candle with a tiny little bulb. Those bulbs that give off like no light at all, that would be a 12 watt bulb for the old school incandescent bulbs. But for the new bulbs, those halogen ones that are spirals, or the other ones that you see that are like a weird shape upward, but they're like the high energy or energy efficient ones, they only use like 12 watts of power. So they consume less energy because the power is the rate at which energy is consumed. Power, delta E over T, the rate at which energy is consumed. Is that clear? So we're going to talk today about electric power, but it's really important that you understand that the power is not the amount of energy that you're actually using, it's the rate that you use that energy. But when you get a bill, you get it from a power company. But the units of your bill, and we're going to talk about this, it's kind of cool, it's not watts, because you can't say you use 20 watts. Watts is a rate. You could say you use 50 joules of energy, right? So the power company came up with their own unit. It's called kilowatt hours. And many of you may have seen that before, heard that term. It's a kWh, kilowatt hour. We'll talk about how that's really an energy unit. Okay, we'll see that today. So let's go ahead and do what we're just talking about. So let's talk first. Let's talk first about what happens with potential energy and the location of the charge. We haven't spoken about this, but we've alluded to it. We haven't gone over like a diagram such as this. So what I want you to do, can I get just someone to read? Simply read. Yeah, go ahead, Honor. And I'm going to point on the diagram where Honor is referring to. So I'll point on the circuit sometime, or maybe sometimes here, but these correlate to each other. A to B here is this right here. B to C across the light bulb is right here. Okay, so follow along as she talks. Go ahead.
A charge will move from a higher electric potential to a lower electric potential, just as we've seen with an object falling from the sky. Higher gravitational potential energy to the ground, lower gravitational potential energy. At the battery terminal point, point A, the potential energy is high, and when it moves from B to C, the energy is converted into internal energy when the filament warms up. When the charge returns to the point D, and the battery does not work on it from point D to A, and as a result, increases the electric potential energy by the same amount of chemical potential energy lost by the battery.
Okay, so what's physically happening here is the concept of energy and conversion. And conservation, really. Right? You're not losing or gaining energy, it's just changing its form. The energy that the charge carriers had in the beginning, that's the potential energy. They went to the bulb. The bulb used that energy, converted into electrical energy. Then those charge carriers returned to this lower potential energy node, at D. And at D, what happened? The charge carriers went into the battery. And I'm making this so simple, but it's not this simple, obviously, right? They went into the battery, they got energy, meaning the battery does work on it. The battery can work on the charge carriers from D to A. Well, where's D to A in the diagram? That just means from one terminal to the other. So in the time of this charge carrier traveling through, it consumed some chemical energy, it gained its own potential energy, the carrier, and then it continued through the circuit again. And this is a cycle. It happens over and over and over again. All right, so this is how we're consuming energy. That's what consumption of energy is. It's power. Okay, but this is the physical process that you're seeing. Pretty simple process if you think about it, actually. Now, what do we constantly try to do? Even though the process is simple, what's the whole idea of engineering? The process may be simple itself, but what do we always want to do with something? Like, for example, this overhead is a new thing, right? What do we used to have? We used to have smart boards. Before that, we had whiteboards. Before whiteboards, we had chalkboards. For chalkboards, we had, I don't even know, they used blackboards, they were called. They were actually black, not green, with the older version. But so what are we trying to do always with something? Even though we know it is simple, what do we want to do? We always want to do something.
Evolve.
Evolve, good. Innovate is the term in engineering, but evolve. Get better with something. So this may be simple, but what are electrical engineers today and research scientists trying to do? They're doing exactly what we talked about to start class. They're coming up with bulbs that are more efficient. They're coming up with ways that save the earth energy, that don't pollute as much, that are maybe something that's more efficient for people around the world that everyone can use, not just countries that happen to have a developed electrical grid. Like, we don't realize how important it is and how crazy it is that, in the United States, you can be guaranteed electricity, like wherever you are. How many of you honestly have plugged in your charger somewhere beside your house? You probably all should raise your hand. I'm pretty sure, yeah, everybody's done that. I mean, if you're not listening right now and doing something else, then you might not know what I'm talking about. Okay, you should have raised your hand there. Everybody has done that. We've all carried a charger whether it's on Amtrak, on a flight, at a hotel, and you're always guaranteed energy, aren't you? Have you ever been like, oh my gosh, there's no power outlets? No, it never happens. Because of the infrastructure of the electrical grid system in the United States, and in a lot of other countries too, obviously, other developed countries. But you go to other countries in the world, and what happens? You cannot plug in, you can't charge, you can't even use internet. That doesn't even exist in some places. So one of the biggest things that some philanthropists and like these great scientists and engineers are doing that have a ton of money because they invented something crazy, and now they're just living off of it. These guys, you know what they're doing? They're saying, we need to make the world a place where there's Wi-Fi everywhere. So soon, believe it or not, New York is going to be completely wireless. Have you read these articles lately? It's incredible what they're doing in New York.
Yeah,
But-
they're turning all the payphones into.
Yeah.
All
There's
those
one
payphone
here.
booths, they're like, you know
Yeah.
what, let's not get rid of them. We'll make those locations. We'll use the infrastructure that's there ready. The power lines that are already there, just got to change the feature of it. So they're doing it in New York, but they're trying to do this around the world now. Believe it or not, Mark Zuckerberg, a few guys like Elon Musk, these guys that do a lot of other stuff, they also do this stuff on the side, and they have their companies putting a ton of money into this, so that they can have these like Wi-Fi hotspots that are almost like satellites over different countries around the world, to give the people in that country some sort of Wi-Fi. Why? Why do you need the whole world to be able to be connected? What's the importance of it? You know some of social studies and social justice? Education. So people are knowledgeable. It's crazy when you think about it. You, since you're a kid, are able to read, you can do whatever you want, parents can tell you stuff, you can learn things. In other countries, people are oppressed. They can't even learn. They have no idea what's going on in their country. They don't know about other places in the world. Think about like places like North Korea that you hear about all the time, where there's like such strict limitations on what their people can actually do and understand. So anyway, the idea of this infrastructure and electricity, the innovation that's going on is really what's important here. Okay, but obviously this concept is quite simple, but it's taking that concept and spreading it out on a more global scale. This is not like a punch or global, this just came up in my mind. I was thinking about how we can actually do this stuff. So we defined this already, but just to have an actual written definition, the rate at which you use energy. Okay, the rate at which you use energy. See if I started here. Yeah. So at this point, let's take a look at our formula. And I'm going to go through a quick derivation. It's very simple. Your book does it more elaborately. I'm going to skip a few steps and show you where it comes from. But the first definition of power, like we were talking about, okay, is the change in energy over time. And we said work over time. Well, that's the same thing, really. This could be thought of, in our case, as potential energy over time, really, because we were talking about the potential energy of the charge carriers. Okay, the charge carriers lose electric potential energy. So that's what power is. It's the change in that energy over time. So this actually can be converted into a simple statement, and this is the parts that I'm skipping. There's like 7 or 8 steps I can show you. It's in your text. You just read through it. It's in this section. So this converts to P equals IV, which is kind of important, but this next step is really what's really important. So this formula is our first formula we're going to look at for power. But what's interesting with power is this. We have a definition for voltage. What is the definition of voltage? V equals what? V equals fill in the blank. You just did it on your quiz on problem 3. V equals what? What was that formula on the quiz? V equals? IR. So you replace V with IR. Let's go ahead and do that. Which makes it pretty much what?
I squared.
I squared R. So there's formula number 2. So this is the formula we're going to use, really, P equals IV. But this formula can be written in a second way. But you know what? It can be written in a third way also. It can be written in a third way as well. What's the third way it can be written? And this one is not as obvious. I'll give you a hint. I'm going to leave voltage this time. Look back up here. Look back up here, please. I'm going to leave voltage alone. So leave voltage alone. Replace what current is equal to. What is the definition of current? V over R. Where did he get that? How did he know right away it was V over R for current? How do you know it's V over R for current?
That's a good guess.
That's a good guess. That's really what you did? Took a guess?
I remember the equation was
It's not a guess then if you remember the equation. What's the equation? V equals, we just said it in the previous one, V equals IR, okay? Solve for I. What's I equal to then? V over R. You just said V over R a second ago. I is equivalent to V over R. Really, if you think about it, look, rearrange Ohm's law. Solve for I. You divide both sides by R, right? You're looking at me with blank stares. This is clear, right?
Yeah.
To solve a formula when it's V equals IR, divide by R. You get I equals V over R. Take V over R and place it here for I.
So V over R squared times R.
Careful. V squared over R. Not V, you said V over R squared. V squared over R. See the difference? Sorry, that's why I was giving you that look. Okay, so it's V squared over R. So there are three ways you can calculate the power consumption if you know something about the electrical parameters involved. So tell me, Pablo, if you know, using these three formulas, right? If you know the voltage and the resistance, which formula would you use to calculate power? If you know the voltage and the resistance, which formula would you use to calculate power? Formula 1, Formula 2, Formula 3? 3. Because clearly voltage and resistance are in this formula, right? If you have current and resistance, 1, 2, or 3? Anybody? Current and resistance. What would you use? 1, 2, or 3? Not 1. 2, right? This is, remember, this is current, and this is resistance. And then the last one would be current and voltage, and obviously, that's the first one. Okay? So in your formula sheet, you're going to see that I think I did something like this. Yeah. Okay? Those are the three different formulas for power. All of them have units, as Frank told us earlier, of watts. Power is a joule per second. Joules per second are watts. All right, let's take a quick look now at an example, and then we'll take a look at maybe something more applicable, like energy, home, power consumption, okay, or energy consumption. So first we'll take a look at a simple example with a TV. The TV is connected across an outlet. It dissipates. What does dissipate mean?
Disperses, it goes away.
Yes, if it goes away, then it does what to the energy? It uses it, okay? It depletes it. So the TV dissipates a certain amount of power. So that's the rate that it's using the energy, right? The rate that it's using the energy. In the form of electromagnetic radiation and sound. Right? EM radiation is light. Okay, it's light, that's what you're seeing. And then what you're hearing is sound. It needs energy for both of those things. Calculate the net resistance of the TV. So here's the thing. A TV has many components to it, right? Each component has different resistance. But as a whole, as an entity, the TV has a rating to it, an overall resistance. So as a result, what we can do is we can calculate the net resistance, meaning the overall resistance. So which formula am I going to use for this one? Which of the three would I use for this one? Yeah. The last one, why?
Because you have V and you have P.
You have V and you have P. Very good. Okay, you have the voltage coming across the outlet of 120 volts. You got the power consumption of 1150 watts. You're trying to find the resistance. So I would definitely choose the third formula for this one. You see how this is kind of easy because you get to choose one of three formulas? So when you're working with power, you need to ask yourself this question. What do I have? Identify your unknowns if it helps you. Or not your unknowns, your givens if it helps you. Start with this and this. Okay, start with those two statements. And then say to yourself, well, you know what? I'm looking for resistance.
You just switch it with power.
Exactly. I can use this formula because it has all three and switch it with power. So let's flip-flop those two. We know we can do that. We've done that a million times now in this class. It's the same formula as V equals X over T. You could flip the V and the T. So resistance equals V squared over power. And I know my units are ohms because everything is standardized and I'm looking for resistance. Number? Come on, calculate. You all got to try this. I know it's simple, but you have to practice stuff. Katie, what do you got? 0.104? Agree, disagree? I see disagreement. Sorry, Katie. Emma? That's okay. Klaus?
12.52.
12.52?
96.
120 squared divided by 1.
You probably...
Oh, yeah, maybe you're
Oh, 1150. I didn't want to.
Sarah, that was very nice of you to say. That only has effect if you use tangent, cosine, or sine.
Oh, shit.
Maybe you're in degree mode. Or maybe you're not in degree mode, like radian mode, right? That's okay. No,
No,
no.
yeah, I meant, yeah, that's what I meant, 'cause it was from math. Yeah.
12.5? I didn't mean to call you out. Sorry. All right, 12.5 ohms. 12.5 ohms. So this is the resistance. This is the rate, not the rate, but the opposition to current. Okay, how much it's resisting the flow of the current. We're going to do a lab, and the bulbs involved in the lab itself, have a resistance of like, I think it's like not even an ohm. It's very little resistance because it's a simple bulb. Okay, it's not stopping the flow as much and using as much power. All right. At this idea of electric power cost. Okay? Now, again, it's going to be called the cost of power, but what is it really? It's the cost of energy. The power is really the rate at which you're consuming energy. So, energy companies, I was mentioning earlier, use this unit called a kilowatt hour. Let's write that down first. And that's how it's written. It's not kilowatt per hour. It's kilowatt hour. They're multiplied by one another to get the amount of energy. Well, let's see that this is actually true. And we can prove that this is true two ways. We can do this with a formula to show it, but I'd rather do it with dimensional analysis. We can convert our units. How do I get rid of, let's see. Well, how do I change kilowatts or watts into something else that we know? So first we can change kilowatts to watts. And then what is a watt? How can we change that? Okay, so we'll start with that. Let's convert that first. So times by. Use your units. Kilowatts are on the top, so they have to go on the bottom, right? And we want to make it watts. How many watts are in a kilowatt?
1,000.
So 1,000 goes.
1,001.
Okay, not divide by. Be careful. It's the other way around. So that gets rid of kilowatts. Agreed. Then, what's a watt really? What can I change a watt into? We've talked about this today like 4 times. It shouldn't be just Anthony raising his hand. What is a watt? What is a watt defined as? Look at the formula for power. The original one from the very beginning of all the slides. From the very beginning. We said power was work over time, or energy over time. So what is a watt really then? What is energy and what is time? What are those units? Energy is measured in? And time is measured in? Very good. So we can replace this now with joules per second. Because that's physically what it is. Is that clear so far? Okay, now I have joules per second. I still have that unit of hour up top. Second is in the bottom. What can I convert my hour to? So it can cancel. How do I convert hour?
Minutes and then seconds.
Yeah, very good. So I'm going to go ahead and multiply. To get rid of hour, put hour in the bottom, put minute up top. How many minutes in an hour, everybody? Thank you. Let me get rid of minute. Seconds up top. So again, hour is gone with hour. Minute is gone with minute. And then lo and behold, look what else cancels. What's the last thing to cancel?
Seconds?
Yeah. Believe it or not, look, that seconds is in the numerator. This one is in a denominator, actually. So what am I left with? Look at it. That's all I'm left with is joules. So kilowatt hours, if I multiply 1,000 times 60 times 60, I get this number. And that's in joules. That's what a kilowatt hour is. So when you get an energy bill, when you get your electric bill, and it says that your home consumed 50 kilowatt hours, you take 50 and multiply it by this to see how many joules of energy you're actually using. So this again reinforces the concept that I've emphasized earlier in the year. Joules are a very small unit of energy. Joules are a very small unit of energy. Look how many joules are in a simple kilowatt hour. And on a home average, people use hundreds of kilowatt hours a month. So you're using a whole lot of joules, aren't you? Because joules are a very small unit of energy. We're going to run out of time for the next one, but I do want to write something else down. Look at the next. See we did. All right. I want to write this equation down first. Cost is energy times your cost per, I should just actually do it this way. I wrote it out in my notes. Cost per kilowatt hour. Okay? Make sense of this for a second. If you want the cost of your electric bill, you can take the energy that you consumed and multiply by the cost per energy, or per kilowatt hour.
Is that just like plugging in 3.6 times
No, so like we're going to do this example. It's a B-day, right? I'm not crazy? Yeah, we're going to run out of time. That's when I want to start it. But we're going to do this. It has to do with putting in how much energy you use, and then you have a certain rating based on where you live. Energy costs different basis where you live. So we'll talk about it tomorrow. Hey, you could definitely look at your homework for this. If there's one of them that's like this, wait, but I think they're both not like this.
Lab's due tomorrow, right?
I think lab is due tomorrow, right? Friday? I have a copy in my office. Just wait 2 seconds. I'll give you right now. So, the idea that we're going to look at here is that the cost for your energy bill is the amount of energy you use times the cost per energy, or the rate at which you're paying. So on your energy bill, what you usually get is some sort of a rating. And you can take a look, it says right here. It says at the very last sentence, if your electrical energy costs 25 cents per kilowatt hour. Okay, per kilowatt hour. So we're going to take a look at an example. These numbers are, by the way, these are factual numbers that you use. We're told in this example that you leave your light on for 3 days. And you say, oh, no big deal. It's all right. It's only a light bulb. It's not going to cost my parents much money. It actually costs a lot more than you would think. Okay, for a couple days for something. Now, obviously, it depends on the actual power that the light bulb is drawing. So we're told here that you leave it on for 3 days. There are five bulbs running, each of which consumes 60 watts of energy. So this would be like a big lamp in the middle of your room. It'd probably be actually less watts because nowadays bulbs are like 20 watt bulbs and they're much more efficient. We talked about this last class, right? Efficiency in light bulbs?
Yeah, we did.
So these are old school light bulbs. They're probably not very efficient, so we'll say they're 60 watt. If the electrical energy costs 25 cents per kilowatt hour, what does it cost you while you're out? Now, first thing first, we need to know how much energy we're consuming. How much energy we're actually consuming. So we have to figure that part out. And how is energy related to power? How is energy related to power? There's your power consumption, right? 60 watts. You can write that down right away. How long are you leaving this on for?
2 days.
How long?
3 days.
3 days, right? You're leaving this on for 3 full days. Now, if I want to think about what 3 days is, I'm going to multiply it by how many hours per day?
72.
Okay, so 3 by 24 hours or 72 hours of usage. Now, I'm going to leave that unit in hours because energy needs to be in kilowatt hours. The reason is, look at the unit of charge. It's the cost per kilowatt hour. So energy should not be in joules in this case. It should be in kilowatt hours. If you recall last class, we talked about how to convert from kilowatt hours to joules, and you guys recognize that it was like 3.6 times 10 to the 6 joules for 1 kilowatt hour. It's a ton of joules for a kilowatt hour. We're going to leave our units in hours because we're looking for kilowatt hours. Now, how many bulbs are running?
5,
So how many watts are you really consuming?
3, 2.
And then finally, last but not least, if my cost is dollars per kilowatt hour, my power should probably be in kilowatts, right? Does that make sense? So I'm going to change my power units now to kilowatts. Well, 300 watts is really 0.3 kilowatts. Okay, 300 watts is 0.3 kilowatts. So I've got my power and I've got my time. I've got my power in kilowatts. I've got my time in hours. Well, it means that I can go ahead and figure out what my energy is. Yeah. How do you know to multiply them? Where did that come from?
Because for every hour, it's 0.3 every hour, and there's 72 hours. So you just multiply them.
It's not 0.3 every hour. Be careful. It's just 0.3 kilowatts. It doesn't say per hour, does it? You're right to multiply them, Theo, but that's not the right reasoning.
Oh, then
Okay.
you multiply them because then you find out how many kilowatts you use in an hour. I knew why it was.
Because P equals W over C, and then if you multiply T over sine.
That's exactly right, guys. It's loud. I know the sirens. Go back to your power definition. In the top right, if you have to, put a little box up here maybe. Power was defined as energy or work over time. So how do I get energy by itself? Theo?
You multiply.
Yeah. So P times T is what energy is defined as really. Take a look at the box in the top right up here, please. Power is energy over time, so energy is power times time. You could also have recognized that your energy needs to be written with units of kilowatt hours. Energy units should be kilowatt hours. And the units of cost or rate, I called this cost the other day, you can call it rate or cost, either one, is in dollars, really, dollars per kilowatt hour. What happens when I multiply dollars per kilowatt hour times kilowatt hour? What do I get? Dollars per kilowatt hour times kilowatt hour. You just get dollars, which is, look, what you want. You want the cost. So whenever you're going to use this equation, or whenever you're going to calculate the cost of an appliance, you're going to be given the rate in dollars per kilowatt hour, and then here you're going to have energy in kilowatt times hour. Well, look, Theo said this is kilowatts, and this is hour. So how do I get kilowatt times hour? I multiply these two. Or, as Emma told us, look at the formula. Energy is power times time. Power is written here, time is written here. 0.3 times 72. We clear? That make sense? So the energy consumption in this case, 0.3 times 72 is going to be the energy consumption. That's going to go in there. Let's write this out. So cost is going to be energy, which is 0.3 times 72 units of kilowatt hours, times the cost per kilowatt hour, which was 25 cents per kilowatt hour. Okay, so I'm multiplying those two things, and I should really put parentheses a little bit later, right? Like that. So 0.3 are kilowatts, 72 are hours, times 25 cents per kilowatt hour. Okay? What do you got? $5.40 for one weekend. It's kind of a waste when you think about it, right? Now, obviously, let's do some quick math. Like I was saying, most bulbs now are like anywhere between 12 and 30 watts. So let's say there were 20 watts. That means it's really a third of this. But still, even with the more efficient bulbs, a third of this is $1.80. Okay, even with the more efficient light bulbs that exist now, it's going to cost you $1.80 just for leaving that lamp on for the weekend. Okay, so when your parents joke with you and say, turn off the lights in the house, they probably do. Some of you that live in suburbs, I assume. If those live in the city, you might not pay your appliance, it might be with your rent or whatever it is. But if you live in a house and you pay your own appliances and electric bill, your parents probably give you a hard time. My dad used to say money doesn't grow on trees.
My mom yells at me all the time.
Oh yeah.
If I leave everything on, and she just like,
When I was a kid, if I left anything on, I got yelled at like no other, like for days. My mom would not live it down, or my dad, both. My dad would I used to work at his deli. If I left the light on for hours, he would take it out of my salary. No joke. He would be like, you left your light on in your room for like 3 or 4 hours today. I'm going to take $1 for salary for next week. Like, what, Dad? But, it taught you a lesson because, money is something that's important, right? So, $5.40. Okay, pretty easy? So you can practice one of these. Let's take a look at this section. You could have done this homework, right? Last night. I don't think either of these, did either of these problems involve cost? The second one? Okay, so finish that one up tonight or this weekend and submit it. Okay, so finish up number 4 if you haven't done it so far and just submit it. So let's load 20-1, please. 20-1.